right? So there's this box, an actual physical mechanical box that you buy off the shelf. You wire this thing in, and what is going into that thing? There is a thermocouple, perhaps, or some kind of a sensing device. In the case of like a temperature control loop, there's a thermocouple. And these things on the output side are just something like a voltage or something like that. Modern devices, something like something that you would plug into your USB port, right? It has become the default that devices have two-way communication. What does this mean? I think it's like, I'm going to go really slowly just because I want to make this point very clearly. But I want you to understand that perhaps your assumptions are different from the way that it would work. If you think about something like a computer, and you think about plugging something into the computer, you always imagine that something will happen, right? Like the computer will tell you it sees the thing, right? Like you've plugged it in, something will happen. There will be an icon, or there will be a notification, or something will happen so that you know you've successfully connected this device, right? This is kind of the default way that computer stuff works these days. There's always this kind of two-way communication. Unfortunately, that two-way communication is considerably more complicated to implement than one-way communication. So for instance, think about really dumb devices in your life. Think about something like a light switch. Okay? When you flip the light switch, there's nothing on the light switch that tells you that the light doesn't work. Think about that. Right? Like the light switch just opens up that switch. It doesn't know. There's no little red warning light that says, hey, there's no bulb in there. Or, hey, the bulb actually isn't giving light. A lot of times we rely on just the simple feedback there that like, okay, when I flipped the switch, the light actually went on. But think about it, there's no communication in that circuit, right? There's just, I pressed the button, and either something happened or something didn't happen, but the button itself can work fine and nothing can happen. And this is the way that the majority of manipulated variables work. This idea that there's two-way communication is called read-back, and it is a very sophisticated control function. Most manipulated variables do not have read-back. And so what does this mean? Why am I saying this when I'm talking about offset? Is I think a lot of you probably imagine that not a bad default would be that the controller simply doesn't move the manipulated variable. Right? So you imagine, okay, I've got my controller, and I want you to think about physically what that would mean, right? Let's say that I'm trying to control flow coming through a pipe, and I'm using a control valve to do that. So this is kind of the picture that we have in our minds, I think, of a control valve. That's the icon, right? But what you have to understand is that this valve literally is a mechanical device. That P that we're talking about is an air pressure, right? So there's an air pressure going in here. It's called P partly, I think, because control valves are such common manipulated variables that pressure is probably a pretty good control output signal. And it's connected to this stem, and it's connected to a spring, and that's all connected, you know, the hip bone's connected to whatever. And eventually there's flow through this valve like this. Right? So that's now a classic ball valve. Notice that for this kind of mechanical system, there is literally no way for the controller to know where the valve is. In terms of, like, at that point in time, the controller outputs conceptually a pressure signal to the top of that valve. Okay? I could move this valve. Usually there are some tuning screws, mechanical tuning screws that I can turn that can move that stem position up and down. Understand that, first of all, it's not electronic. Second of all, those things aren't connected in that way. There's no way for the controller to know where the valve is. And so if you think about something like if a very simple strategy, like, well, I turn the controller on and all it has to do is not move the valve. How would it do that? To not move the valve, it would have to know where the valve is, right? So in most cases, if you're just working with relatively simple manipulated variables, there is no way for the controller to know where the output is when it gets turned on. Because most outputs don't have read-back. These components aren't connected by USB, right? They are connected by the pressure in a tube. And in fact, those things are downstream connected by mechanical linkages and stuff, which have no electronic read-back at all. And I suppose this is getting harder and harder to imagine in a modern time, right? Like you imagine that people sitting in a control room have measurements that indicate the complete state of the plant. But literally, in many cases, the only way to know things on the plant is to pick up a walkie-talkie and walkie-talkie the guy, the man who is out in the plant and say, hey, can you go and look at vessel 302? What is the level looking like over there? Look at the gauge that is on that vessel and tell me what you see. Now, I can see this is a surprise to most of you. But, it's surprising relative to kind of, let's say, the modern Internet of Things kind of version of reality, right, where everything's measured. The fact is that all of those measurements cost money. And the reality is that if you can save money by not having that measurement, if you can save money by having a slightly more stupid control valve than the clever, smart instrument that costs twice as much, why would you pay twice as much for an instrument that does the same thing if most of the time you don't need to see it? So you have to understand that on the typical control plant, the typical control plant does not even have enough measurements so that you can check whether the mass and energy balances hold on your plant in the control. I've spent many years working on control for reactors at Anglo. They have temperature control loops where the temperature control is handled by steam. The steam comes from a common header. It goes through a control valve. Nobody on site can answer the question, how much steam are we using in this reactor? Nobody can answer that question. Why? Because they don't need to. They just need to know whether they're getting the right temperature and whether the whole plant has enough steam in total. If the whole plant is using too much steam, they need to put in a bigger boiler. But they don't actually have separate flow measurements for every place where they use steam. Most of the time, they don't have separate flow measurements for all the places where they use cooling water, right? They just use enough cooling water that they get to the temperature that they want to get to. They've got a big common cooling water supply. All the cooling water comes from the cooling tower, goes through all the places where you use cooling water, it goes back to the cooling tower, and the problem is only when we have outstripped the capacity of the cooling tower, then we have a problem. But most of those things aren't measured. And it shouldn't actually surprise you, right? Because can tell me truly, not like because it's on the label, but if you turn on your kettle, if you turn on a light bulb in your house, if you turn on your oven, how much power is that using? Oh, you don't have gauges. You don't have gauges like on everything that tells you how much power, every electricity consuming device in your house, right? You can't tell me how much duty it's using. So how would you do an energy balance, right? Like how would you do the sum that tells you how long it's going to take to boil your water if you don't have that measurement? Well, you just don't have it, right? So what you have is, well, I turned it on. I know that it gets hotter when I turn it on, so it's still working. I have no way of knowing the element has over time lost some duty, and now it used to be a 2 kilowatt element, but these days it's corroded a bit, so actually it's like 1.5 now. This is facts, okay? This is normal equipment. So you first have to understand how dumb these things are. And every year, this part of the lecture gets longer because your assumptions get higher and higher. you imagine that normal operation is incredibly complicated. You think Facebook is like a normal website, right? It is a website built by the most highly paid web development team in the world. It is not a normal website. It is like the pinnacle of website technology. If you measure your other experiences against Facebook, you're going to have a pretty tough time because nobody can do that work, right? If you think like cell phones that communicate automatically to the devices around them and Bluetooth, that kind of stuff is normal technology. It is completely not normal technology. The same thing, this valve will cost maybe 15,000 Rand. A smart version of that will cost 100,000 Rand. Right? A little gauge, if I'm talking about control, right? If I put in a gauge like a mechanical thermometer, when I say a mechanical thermometer, one of those things that you learn about in CIR2, right? Where it's like either like an ethanol or whatever. Those things cost nothing, less than 20 Rand, right? To install them on site, maybe a couple of hundred. To install the same thing with a thermocouple and a transmitter and wiring all the way from where it is to the place where it needs to go and power and so on, right? Costs maybe 20 times more, maybe 50 times more. And you are a poor engineer if you can just say, well, I know we can do this for 50 times less money, but it's really cool to know, like where everything is. I think it's just nice to have those measurements, right? You will hear me say this many times. It's your job as engineer to install the cheapest thing that does the job. That's your job. Anybody can build super expensive stuff that works. That's no skill at all, right? Just pay somebody else to do all the work for you and skim off some at the top, right? That's an easy job, right? It's really hard to build it lean. And so this is why these pieces of equipment are the way they are. So you've got to relax your expectations. I've told you that you shouldn't be thinking about a little man in the controller, right? Like you shouldn't be thinking about the controller having really like a brain. Because at the very basics, right, this is like, I think just that equation by itself is like 60% of all installed controllers in the world. Okay? Which is like a resistor and a capacitor and some knobs. It's not making decisions, it's not doing calculations, it's not doing anything particularly sophisticated, it's just doing that. It's writing out, it's never even checking whether the valve actually did what it wanted to do. The best it does, right, the closest it gets to that readback is to read the actual control variable. Right? Because it does, in some sense, know. And, I used to be very loath of using words like no. I took great care not to do that. But it does help to think about it in that way a little bit. But how does the controller know that it's actually done something? The only way that it knows is when it reads back and sees, oh, okay, yes, well, so that had this effect. Conceptually, otherwise, we don't know whether the actuator has been stolen or whether it's kind of stuck somewhere. All of these things happen. None of those things typical controllers would know. There's no light that comes on. There is PhD level research on knowing these things without having a button or like a... By saying, okay, we saw that the controller asked for the valve to open and then 5 minutes later the flow had not yet increased. So maybe that means there's a problem in the system. This is how it works. So, the plant is not a smart system, right? It's valves and tanks and pipes and so on. The actuator typically is a very dumb thing by itself, and the controller is also dumb. And they are not talking back and forth, they're always just talking in one direction. So I measure a temperature, and all I know is that the temperature changes. I don't know why, I don't typically know whether that's a reliable measurement. I just have this number. I just have this current in a wire. So hopefully now it becomes clear, in terms of application, why it would be that we need this and why that would be on the controller, because you set that on the controller. You turn that dial on the face of the controller to say, right, I'm going to tune this controller just like so that the output is valve halfway open. And nothing about that system, typically even these controllers will perhaps be smart enough to kind of remember their personal history or like their settings, but most of them will, for instance, not like carry over the integral, for instance. And they're definitely not remembering, the controller itself is definitely not remembering all of the inputs from the past. It's carrying that, it's a capacitor, right? Like it's not a special system. The charge in the capacitor or the loading, the voltage on the capacitor just tells you what the integral of the current was that went through it. That's it. And so when you turn it off, that just goes away. And then you turn it on again and it's like wiped clean and you just keep going. So I keep drawing all of these pictures and I think it's hard. I'll try and get some controllers, but it's hard to picture these physical controllers because these days, most controllers are, and I mean, I'll say that straight up. Most controllers, definitely the ones that you can buy easily now, will not be made out of capacitors and relays and so on. They'll be made out of, well, they'll have a little chip on them. But it'll be a really cheap chip that will do very little. It will still be very basic. I will try and see whether I can get a control valve from the lab for us to look at today during today's TUT. So I want to summarize where we are now in terms of PID. And I want to just use that as the entry into derivative control. So remember yesterday we talked about proportional control. And if you remember the analogy that I was using of kind of the garden hose situation, later on I discovered different people hear what I'm saying in slightly different ways, so I want to restate it again. When Walter shouts at Tamara, and she has a particular position in mind based on that volume, this is the proportional action. And what I also realized is that most of us don't actually work that way, right? Most of us will turn faster based on the volume rather than have some kind of position in mind. So that position, I'm just going to say, he's shouting about this loudly. I'm going to move the valve exactly to this position and just stop. That is proportional action. Now, remember what that formula is actually like. So proportional, right, has this, the error has made a single change. So I will make a single change in my, so if that is delta epsilon, then this is delta epsilon times Kc, and this is P bar. And this is proportional control in a nutshell. This is the way that proportional control works, right? Is when the error makes, or at every position for the error, there is an associated output. There's no movement in that picture other than the measurement changing. So the only reason why a proportional controller would ever change its output is because the inputs have changed. It doesn't have dynamics. It is just a simple gain. And so what this means is he shouts, she turns to that particular new position. The only reason why she's making a different turn is because the volume of shouting has changed, right? Integral is a lot more like what most of us would do, which is I will turn the tap at a rate that is proportional to how loudly they're shouting. Right? So when they're not shouting very much, I won't turn very fast. I don't have a specific position in mind. I just know if they say keep opening, I'll keep turning clockwise. If they start saying close, I'll start turning counterclockwise, right? And so this is why I was saying that that valve, the tap, remember, integrates to position from rotation rate. And so if your strategy is to do this, right? To say, I'm going to wind open the valve when the error is high. You're effectively doing integral action when you measure all the way to the position of the valve. Right? So you're using the valve as the integrator. So if you are determining the rate at which you change the manipulated variable based on the value of the error, you end up implementing integral action. So proportional action goes from the error, from a value of the error to a single position on the output side. Integral changes the rate at which it changes the variable based on the value of the error. When the error is high, the output changes at a high rate. When the input is, the output changes at a small rate. Right? So integral action means that the error changes the rate. Action means that the error causes a every value of error has an associated output value with no. The only reason why we get these curves with proportional control, right? Remember, we do get these curves where as the flow gets up, is because Walter is shouting less loudly. That's the only reason why we're closing the valve in that case. But with integral action, the measure is fixed. And I'm still changing my manipulated variable. Why? Because the error is still accumulating into that integral. Right. So then there is the last piece, which is derivative. And remember that we can't build an exact derivative unit, right? So like the ideal derivative has this ideal step response, which is like super sharp pulse followed by nothing. And most of the time we'll implement this. The approximate output of a derivative-only controller would just be that pulse. If I had a sudden change in the error. Now, what this is like, and again, I'm trying to build this analogy, is at moments where you realize there are large changes in the error, you want to be able to counteract those large changes immediately. If you notice that something is changing at a high rate, you want to counteract that. And so a derivative unit has this, obviously the opposite version, or if an integrator takes the error and sets the rate, a derivative unit takes the rate and sets the error. Does that make sense? So a derivative unit will say, oh, the error is changing at a rapid rate. And when the error changes at a rapid rate, it will have a fixed controller output in mind that corresponds to that. So this is now, if I'm doing a step response, that's what that looks like, right? Step in E. But this rate version is saying, if suddenly the output starts changing at a certain rate like this, right? A derivative controller would have that kind of output. It would move from where it was to a new place and stay there. Is this making sense to everybody? I've just drawn a derivative there, guys. So I've just drawn the input is changing at a particular rate, and if that rate becomes higher, then that output becomes higher. Right? If that rate becomes less, then that output becomes less. Now remember, these last two modes are almost never used in isolation. It's a PID controller, and usually there's almost no way to buy an off-the-shelf controller that doesn't have a proportional action. So every PID controller will always at least have proportional action. These idealized versions where I say, well, this is what an integral-only controller would look like. This is what a derivative controller would look like. Remember, these are the base cases, and then typically we will add them together. So the realistic versions of controllers are P, PI, PD, by approximation, there are no other PID controllers. They all have proportional action, and then, so you start with proportional action, and you think, what should I add to this proportional action to make control better? Am I seeing a persistent offset? Yes. Maybe I should add integral action, which will reduce that persistent offset to 0. Only in cases where that's a big problem. There are plenty of systems like tanks where exact level control is not particularly important. It's important that it doesn't overflow, and it's important that it doesn't go below some certain level, but it's not super important that it has to be exactly at 50%. If it gets to 55, not a big deal. Awesome, I can save some bucks by putting in a simpler controller. I don't need the fancy controller that's always exactly on set point. In fact, I might be getting a lot of nice things out of that because I can use that tank to absorb variations in the system, which I'm not worried about. If I find that there are routinely rate changes in the error, but things drift over time, you can accommodate that drift in some cases by adding derivative control. Derivative control also, when you think about the rate at which proportional control can take action, proportional control acts immediately when the input changes immediately. Derivative control can act immediately when there is a large change in the rate of error change. Now, a proportional controller in this case would make, at that moment where you can see, okay, everything was steady, and then suddenly the rate changed. A proportional controller at that point in time would do nothing. Right? Because the error hadn't actually changed much in magnitude. But a person would say, wow, that's changing, and it's changing a lot. Like in a short time, it has changed a lot for that short time. Maybe I should take some anticipatory corrective action instead of waiting for the output to actually get really bad. And so you'll see this is why derivative action is usually or often called anticipatory or like look ahead or something like that. Right? So it involves this idea that calculating derivatives is actually a little bit like looking into the future. Because we're kind of making a prediction that if this were to stay on that trajectory, it would get bad quickly before we would have time to make that accommodation. And derivative action, also another very important thing to know about derivative action, especially when you look today at the tutorial activity. Of all the parts of PID control, derivative action gets the most benefit from the ideal analysis that we will be doing mathematically in this subject.